based, he's a full-time employee in a partner company. So he's going to explain all of that. So off you go, Patrick. Thank you.
Okay, thanks Siobhan. So my name is Patrick Ruane. I work in Johnson & Johnson Vision Care. I have a slide here that will give a little brief introduction of what we do. I'm currently doing a PhD and I'm on my last year in TUS in Limerick. And J&J Vision Care is also located here. I show on the red arrow in Limerick, Ireland. These are my three supervisors, and they've provided fabulous support over the last 3 years, so in directing and coaching and guidance on my PhD. So thank you very much to Paddy, John and Siobhan. My PhD title is a research project is the application of a hybrid simulation approach to aid the design and development of an automated manufacturing line. A little bit about myself. So I work in Johnson & Johnson Vision Care, and J&J, we design and manufacture vision correction contact lenses. We're the largest contact lens manufacturing company in the world, with 2 sites, one in Florida and one in Ireland, in Limerick, Ireland. Some of the products that you may recognize here on the left-hand side or on the right-hand side, so it's all of the AccuView range of contact lenses, one-day disposables and reusable lenses. In my position is a special projects director, and I responsible for the design and development of the automated manufacturing lines for these contact lenses. And some of my personal motivation for doing a PhD is develop expertise in simulation and optimization. And there's also a personal desire to continuously pursue new learnings and deliver a new approach and system to the business, and also then to aid in further my career advancement within J&J. A little bit about the technologies that's in Johnson & Johnson Vision Care. So we have fully automated manufacturing lines, and these would be, they would take the raw materials automatically onto the line, and the manufacturer inspect the contact lens without it ever being touched by a person. And it comes out the end of the line and is cartoned and case packed off. Some of the technologies that would include there is injection molding machines, dosing systems, curing systems, a lot of robotics, a lot of sensors, sterilization, packaging is all controlled by programmable logic controllers. To give you an idea, you know, a line would cost in excess of $30 million. And some of the primary key performance indicators, you know, obviously quality and safety, but also then lenses per shift coming off those lines. A little bit on the research. So based on an extensive literature review that I've done, a lot of industrial experience, some management feedback, and discussion with original equipment manufacturers, some of the 4 significant issues were identified. So reduce the overall time for manufacturing equipment delivery, reduce the time for the design of that equipment, and a system/approach to verify concept designs for continuous improvement. So we have a lot of lines in the plant, and we continuously improve those every year. And when I say improve, is to improve the quality and the throughput coming off the lines, and then a system to aid in predicting line capability for production planning purposes. So a little bit on the research introduction. So I have investigated the use of simulation and optimization approaches that are, you know, out there in both in industry and academia, and with the aim of using these digitalization technologies to optimize what I call a tray loader system. So this is part of the contact lens manufacturing line at Johnson & Johnson Vision Care. And the research, my research combined simulation using a JAMSIM simulation package with an optimization engine. And I'll talk a little bit more about those as I move on. The digital model, which was developed, what I developed using JAMSIM, was derived from the real world automated manufacturing line, which is the tray loader system. And the model was integrated, so I integrated the model then with two different optimization engines. One, namely SimWrapper, and I'll talk a little bit about that one later on, and an optimization engine that I developed myself using popular genetic algorithms. And the overall system was designed and developed to demonstrate and evaluate the use of digitalization to support the design of automated manufacturing lines. Some of the, what are, like, and one would ask, why would you do that? So these are some of the, I list out some of the advantages in doing that. So we can test different scenarios using the digital model. When I say different scenarios, if we want to make an improvement on the line, we can test that scenario out on the digital model first and see what performance improvements we can get from making that particular change. Test new line designs early in the line development process. So if we come up with a new line design, then we can test that before we start building the line. And then also determine what the impact of workstation changes, i.e. cycle time, mean time between failure, mean time to repair, on the overall line performance. And number 4, determine the optimum line conditions to run the line. And these then have the impact of reducing the design time and the time to market significantly for us, particularly, which is in JJVC. And lastly then is to reduce the impact of making line changes before and after factory acceptance test. And that's a test we do at the vendor site before we accept the equipment. And secondly, at the site. So we install the equipment in our site and we perform a lot of tests on that equipment. And so this system of developing a digital model and optimization reduces the impact of making changes before and after those particular tests. And then it's a valuable tool for engineering to use in the manufacturing line development. So when the line is in operation every year, as I mentioned, we make improvements on that line. So these tools are a valuable aid for engineering to test those improvements before you put them on the line. A little bit on the actual system itself. I'll just quickly go down. So there's a product feeder here. So we take contact lens arrays and we pick them up and put them onto a conveyor, which is the grouping station. And we group them then into groups of 10. We load them into a plastic tray, which is this one here. And those trays get stacked into groups of 15. Then we group two groups. We group a stack of 15 into twos, and they either enter into a process station 1 or 2, which are these two particular stations are sterilization chambers. Product is sterilized, it comes out, and we unstack the stack into individual trays again. Then we go into process station 3, which it's a drying process to dry off any moisture on the arrays. We unload the tray, take the product out of the tray. Then we group it into 30s, and we pack it off into cartons. And then finally, we case pack it off into corrugate cases, and from there it goes off to the warehouse or to distribution. These empty trays then go back into a buffer, ready to get reloaded again, and the process continues. So I developed, first of all, a digital model using JAMSIM of that whole particular process, and included, and so you can see all the various stations here as the product is moving through the tray loader system. Also put in downtime entities, and you can see them here in yellow, for the various workstations on the line. And then on the right, further on the right here, is the distributions of mean time between failure and mean time to repair for each of those workstations. Just blowing it up a little bit. So this is what the digital model looks like when I developed it in JAMSIM. That model, then I validated that model to ensure that the digital model was an accurate representation of the actual system on the line. And to do that, I collected data from the line. So it's every shift over a 3-month period. We run on a 24/7 operation. And the types of data that I collected was throughput and yield from the various workstations. Also collected the uptime for every station on that trail loader system over 129,000 minutes. So a lot of data to analyze. And once I analyzed that data and determined what the various distributions were for the input rate into the line, the yield, the mean time between failure for each of the workstations, the mean time to repair for each of the workstations, I plugged all that data and distributions into the digital model, and then run the digital model and compare the results of the digital model to the actual line, and have shown that statistically the data from the simulation model or the digital model has a prediction error of approximately 0.2%. So it's a very good representation. That digital model is a very good representation of how the actual trail loader system performs. So once I have that done, this is, it's the digital model. What I ended up was this type of a system. So I have a file where I can change the input parameters for the simulation model. The simulation model then takes those parameters, runs the simulation, collects outputs, and then I analyze them offline. And if I want to I analyze the results offline. If I want to make further changes or further tests, then I update the input parameter file, rerun, and analyze again. So it's a very slow and cumbersome process. And for an optimization system, you can run a couple of experiments, but you can't do hundreds and thousands of different experiments because it's too slow. So I came up with a strategy then of developing an optimization engine where this whole thing is fully automated. So I have the input parameters, I run the simulation, I collect the outputs, I analyze those outputs, and then recommend new input parameters, and then rerun again. And that loop continuously runs until I exit. And I exit when the optimum conditions are obtained or a specific termination criteria is achieved. And I list out some of the benefits and what the actual process is. And the process is kind of pretty much as what I described there. And to give you, and you might wonder, well, why would you do that? And for this particular trail loader system, I have 7 factors that are important on how the system performs. And each of those 7 factors, I can run at between 21 and 31 different levels, i.e. different settings. And if you take all of those factors and all of the settings for each of those factors, you end up in excess of 2.6 billion combinations that you could run this piece of equipment at. And as such, it's impossible to find an optimum solution using the standard techniques. And that's where an optimization engine comes in. 2 of the optimization engines I use one off the shelf called SimWrapper. SimWrapper, it supports constrained or unconstrained optimization with many objectives. The architecture, I won't go through this in detail, but there's an architecture I developed for integrating SimWrapper into use and the digital model. So I have the input data pre-processing of the data. This is the optimization loop here. And then once I terminate, I get the results and analyze those results. Some graphs that I show here, these are some of the graphs here for, I want to maximize the number of trays, maximize the output from the line, maximize the process 4 output, minimize utilization. So these are, it's over 120, 100 simulation runs here, and these are the types of results I can get. The other system then was using genetic algorithms. And genetic algorithms it simulates the process of evolution, and it's based on Darwin's theory of natural evolution. And several GA configuration parameters are required, such as population size, crossover, and mutation. And then I determine what the fitness value. I run particular solutions and calculate or determine using the digital model the fitness value, i.e. the output from the system. And then using genetic algorithms, recommend and updated parameters to rerun the next simulation run. Similar type of architecture. So input data pre-processing, the optimization loop here. And then once I terminate the optimization, then I analyze the output data coming off that run, those runs. A little bit on the results. So this is a typical results that I generated from optimization run number 1. And you can see here, so I plot this out on Minitab, and within each generation, so I've run the optimization engine for 50 generations, and within each generation, there was approximately 100 solutions within each generation. And I can see here, the blue line is the maximum P feeder output, the green is the minimum, and the red is the average. And I can see as I'm going from one generation to the next, the maximum optimum solution doesn't change, but all other solutions within that generation are getting closer to the optimum. Another way of looking at it is the standard deviation within each generation is getting less. So what this is telling me is I've reached the optimum solution. So the solutions that were used in the digital model to generate these outputs is the optimum solution for that particular setup. So that was for a single objective optimization problem, and the objective here was to maximize the P feeder output. Similarly, I do the same for a 2-objective solution, and I can see that both SimWrapper and the genetic algorithms are giving me similar type of solutions here. So I want to minimize the tray count and maximize the P feeder output, and I'm getting these types of solutions here on a Pareto front. I do a similar type thing then for 3 objectives, i.e. minimize the tray count, minimize the trays used to maximize the P feeder and process 4 output. So I can see here on the left is the results I'm getting using SimWrapper, and on the right is the results I'm getting using the genetic algorithm optimization engine that I developed. A little bit on the research summary. So the use of a digital model of a tray loader system was developed with a prediction error of 0.2%. I also did work on developing a meta model and how this model can be used very quickly to show the impact of line parameter changes. As I explained, optimization system was developed using a black box SimWrapper and genetic algorithm. The genetic algorithm optimization engine allows user so the user can configure specific parameters within that for whatever type of application problem they have, and allows for further refinement to obtain better results. A list of some of the publications that I've developed or written over the last 2 years. And that's it for me. Any